Good day and welcome to our lecture on Group 2 elements, which are also known as the alkaline earth metals. The elements belonging to this group are beryllium, magnesium, calcium, strontium, barium, and radon. The last one is very rare and radioactive. Beryllium has not been marked in the same color as the other ones because it behaves quite different compared to its heavier homologues. In this depiction, you can see the metals in their elemental form and the fact that strontium and barium are stored either under oil or in a glass ampule underpins their high reactivity. The alkaline earth metals have common properties which are summarized in this particular slide. Their common electronic configuration is Ns2. Generally, their properties are very similar to group 1 metals, but they are harder, denser, and less reactive. Their common oxidation states are 0 and +2. And for example, you can have beryllium 2+, magnesium 2+, and calcium 2+ as very common cations. Due to their high reactivity, they do not occur in nature in their elemental form. The group name is derived from the fact that the hydroxides are basic. However, the relatively low solubilities of these in water makes the elements more like the typical earth metal aluminum to their right. Beryllium is quite different from the rest of the group and resembles aluminum, which has been described as the diagonal relationship. The physical properties of group 2 elements are summarized in this slide. You can see that the melting point, boiling point, and the density do actually not follow any particular trend. On the other hand, the first ionization decreases down the group, and the sizes of the atoms and ions increase down the group as expected. The steady increase of their sizes is also highlighted in this particular figure. Moreover, their standard reduction potentials decrease down the group, and again you note that all their standard reduction potentials have negative values, which means that they are very electropositive and easy to oxidize. Some common properties of their compounds are summarized in this slide. In general, the ionic character of the compounds increases down the group. The first element, beryllium, forms highly covalent compounds which are generally sp3 hybridized. On the other hand, magnesium forms already more polar compounds, and the even heavier homologues form ionic compounds. The oxides and hydroxides become progressively basic down the group. For example, barium oxide and barium hydroxide are actually amphoteric. Magnesium oxide is basic and magnesium hydroxide is weakly basic. The oxides of the heavier homologue calcium, strontium, and barium are basic, and the hydroxide are strongly basic. The thermal stability of the carbonates, nitrates, and sulfates increases down the group, which is a common behavior we have already seen for the group 1 metals. Now let's focus on beryllium. The name beryllium comes from beryl, which was considered as a precious stone. And examples of these precious stones are aquamarin, emerald, and many others. The element was discovered in 1798 by the French chemist Louis Nicolas Vauquelin. Beryllium is the second lightest metal and is hard and brittle. Beryllium is one of the rarer metals. Most common minerals are beryl and bertrandite, which have these particular formula. Pure beryllium, which has the highest melting point in this group, is depicted here. In this figure, you can see 3 varieties of beryl: morganite, aquamarine, and heliodor. Emerald, another example of a beryl, is depicted here. In particular, emerald is a chromium-containing beryl. And finally, we have a depiction of bertrandite. So you can see here that beryllium can form very nice minerals and gemstones. Since beryllium doesn't occur naturally in its elemental form, it needs to be produced by redox chemistry. For example, it can be produced by the reaction of beryllium fluoride, which contains beryllium in the +2 oxidation state, with magnesium, and in this particular redox reaction, the magnesium donates 2 electrons to the beryllium, reducing it to elemental beryllium, whereby the magnesium is oxidized to a 2+ cation, which then combines with the fluoride to form magnesium fluoride. Alternatively, you can conduct an electrolysis of barium chloride, and the addition of sodium chloride ensures a reduction of the melting point to about 350 degrees Celsius. Again, you are making use of a eutectic mixture. Now, beryllium fluoride or barium chloride in turn are obtained from beryl or bertrandite, which are the minerals we have seen previously. Pure beryllium is used as a construction material for nuclear reactors due to its very high melting point, and it is also used as output windows for X-ray tubes. On the other hand, beryllium alloys are used as material for construction planes and surgical instruments. We have already mentioned that the chemistry of beryllium is very different from the rest of the group. That is due to the beryllium 2+ ion being highly polarizing, and because of that it forms highly covalent bonds. Beryllium and its salts are highly toxic. Inhalation of either the element or its compound as vapor or dust causes lung damage, which is usually fatal. In lower dose, the element is carcinogenic. Now let's look at the beryllium-aluminum diagonal relationship in a bit more detail. Now, beryllium and aluminum form both covalent hydrides. The halides and oxides are also more or less covalent, and that is different from compounds that are formed by magnesium, which are highly ionic. Barium chloride, for example, and aluminum chloride are very sensitive to hydrolysis. They can be sublimed and act as Lewis acids, being soluble in many organic electron donor solvents. Magnesium chloride, on the other hand, is an ionic compound. Beryllium and aluminum form amphoteric oxides, but magnesium oxide is basic. Beryllium and aluminum form carbides that contain the C4- anion, whereas other group 2 carbides contain the C2- ion. As mentioned, barium oxide and barium hydroxide are amphoteric, which means they dissolve in strongly acidic and basic solutions. You can obtain barium oxide by two general routes. You can simply take beryllium and burn it to form barium oxide. That is a reaction with oxygen, and obviously that is a redox reaction. On the other hand, you can also simply take barium hydroxide and heat it to eliminate water under formation of barium oxide. Similar to aluminum hydroxide, barium hydroxide is a white gelatinous solid that can be prepared by addition of a base to a beryllium salt solution. The reaction is depicted here, and so you simply have a reaction of a barium 2+ cation with two hydroxide anions to form barium hydroxide, which precipitates from solution. Now, if you take the barium hydroxide and you treat it with a strong acid, then dissolution of that species occurs and you form a tetra-aqua species. So this is your aqua complex. On the other hand, you can also dissolve barium hydroxide in basic solutions. So by addition of additional hydroxide, it is proposed that you form this tetrahydroxidoberylate. Although proposed, this berylate has been elusive for a long time. This slide shows the different stages in the search for berylate. The tetrahydroxidoberylate anion has been postulated as the dominant species in strongly alkaline solution of pH 12 to 14. It precipitates with various counteranions, and here you can see a formula for a proposed calcium salt of berylate. This one was crystallized, however, the structures could not be determined. Only in 1998, Hubert Schmidbauer discovered that berylate crystallized from sodium hydroxide solution at pH 13.2. However, the structure determined did not reflect the beryllium central atom with 4 hydroxide ligands. But on the other hand, it forms this particular tetranuclear dianion, which has an adamantane type structure. The structure you can see here, so that is very similar to the adamantane molecule, which is an organic molecule. Finally, in 2011, the structure of this particular compound has been established. So here you have a strontium salt, which contains actually the berylate anion. And the structure is shown here. You can see the beryllium in the center, surrounded by 4 hydroxidoligands. And this 2- anion is further stabilized by additional strontium cations. These strontium cations obviously have interaction with the hydroxido species. So this is just one small unit of this structure. Here you can see how the tetrahedrons are interlinked. And in this particular depiction, you can see the arrangement of these tetrahedron in 3 dimensions. Other notable barium 2 compounds include barium hydride, tetrafluoridoberylate, beryllium nitride, and beryllium carbide. Like boron chloride and aluminum chloride, beryllium chloride is a Lewis acid which forms adducts with anions on neutral electron donors, such as chloride, ethers, and ketones. Here you can see the structure of these compounds. In all cases, you have a beryllium which is sp3 hybridized, giving rise to a tetrahedral complex. Here you can see 4 chlorido surrounding beryllium, and since chlorides are negatively charged, beryllium is 2+, you have a remaining 2- charge. If you replace 2 of the chlorido with neutral ethers, then obviously you obtain this tetrahedral compound, which is neutral. And you have a very similar compound formed with ketones. Beryllium salts, upon dissolution in water, will form aqua complexes, and the structure is depicted here. And again, you have a tetrahedral arrangement of the water molecules around the central beryllium 2+ cation. Since water is a neutral molecule, you have a 2+ charge of this tetrahedral complex. Very similar, if you dissolve beryllium in ammonia, you get a tetrahedral amine species, and this species also has a 2+ charge. Previously, we mentioned that beryllium fluoride and beryllium chloride are obtained from beryl as a starting material. Here you can see the reactions involved in this particular process. You take beryl and you treat it with concentrated sulfuric acid, which leads to the formation of beryllium 2 sulfate, and of course you have aluminum sulfate as byproducts and some silicates as well. Now you can take this beryllium sulfate and treat it with aqueous ammonia, whereby beryllium hydroxide precipitates as a white gelatinous solid. When you take this compound and you heat it up, then you dehydrate it to the beryllium oxide. And this beryllium oxide can further be treated with carbon and chlorine gas to obtain beryllium chloride and carbon monoxide. Now this particular reaction is a redox process in which the carbon has been oxidized, but the chlorine gas has been reduced to chlorides. You can also take the beryllium hydroxide and convert it into tetrafluoridoberylate with ammonium HF2. So in this particular case, the ammonium will form the cation for the tetrafluoridoberylate. Upon heating, you simply eliminate ammonium fluoride, and what remains is beryllium fluoride. Beryllium X2 type compounds have very unique structures. If the ligand X in beryllium X2 has more than one lone pair, which is the case for beryllium chloride, then a polymer BX2N with bridging ligands can be formed. For example, beryllium chloride in the gas phase at about 1000 degrees is a discrete molecule. It is linear and has discrete beryllium chloride bonds. So you have individual BeCl2 molecules. If you condense beryllium chloride into a solid, then polymerization occurs. Here you can see the Louis structure of this polymer. All the beryllium atoms are bridged via chlorido bridges to their neighbors. And the chloride ligand is capable of doing that because it has essentially 4 lone pairs, and it utilizes 2 of these lone pairs to bond to the 2 adjacent beryllium centers. Now, if you look at the polymer in this direction, then what you can see is similar to this. So you have a beryllium center, and going into the screen, you have 2 chlorido ligands, and 2 other chlorido ligands are actually pointing out of the screen. Overall, each of the beryllium is still tetrahedral in geometry. Now, this polymer is electronically quite different from the polymer of beryllium hydride. We have learned previously that beryllium hydride actually forms a polymer under formation of electron-deficient 3-center 2-electron interactions. And that was due to the fact that the hydride only contains 1 lone pair. Chlorides contain multiple lone pairs, and so it can form normal 3-center 4-electron bonds. Again, we can look at this depiction. You have 3 centers, beryllium, chloride, and beryllium. And the chloride utilizes 2 of its lone pair, which contains 4 electrons, to form this interaction. So overall, you have 3-center 4-electron bonds, which are pretty normal bonds. So the bridging chlorido ligand donates 2 electrons to each beryllium center. Overall, it acts as a 4-electron donor. Smaller beryllium hydroxides behave in a very similar way, because alkoxide contains 3 lone pairs. So if you have a compound with a small alkoxide like methoxide, then you have an analogous polymeric structure as observed for the beryllium chloride. However, you can tune this kind of structure by increasing the alkyl group. So if you change the methyl group to a tertiary butyl group, which is significantly larger, Then you do not form a polymer anymore, but what you observe instead is the formation of a trimer. And that is because the tertiary butyl groups here are so large that formation of a polymer is sterically less favorable. Now, if you make the alkoxide even bigger, and in this case you have a phenoxide containing 2 additional tertiary butyl substituents, then you can actually form a linear monomeric compound containing only 1 beryllium center. So again, you can have a steric control, and by increasing the size of the ligand, you can obtain very different structures. Now let's look at the chemistry of magnesium. The main magnesium is derived from the Greek area magnesia. Manganese, magnetite, and magnetism were also named after this area. The element was discovered by Scottish chemist Joseph Black in 1755. Magnesium is a silvery, shiny light metal with a melting point of 650 degrees, so its melting point is substantially lower than that of beryllium. Magnesium makes up about 2% of the Earth's crust, so it's a rather abundant metal. Because it's very reactive, it is not found in the free state, but only as magnesium 2+ cation in salts, and particularly in carbonate, silicates, chlorides, and sulfates. The first preparation of magnesium by electrolysis was again achieved by Sir Humphrey Davy in 1809. Here you can see a depiction of the shiny magnesium in its elemental form. So how do you make magnesium? Again, we have mentioned electrolysis, and in this particular case, you use molten magnesium chloride and you mix it with alkali metal chlorides to make use of the eutectic mixture. In this particular case, you conduct the electrolysis at around 700 to 800 degrees. And so you essentially just reduce the magnesium 2+ to magnesium, and you oxidize the chlorides to chlorine gas. In spite of its great affinity for oxygen, magnesium is rather stable in air at room temperature. It is applied as an alloy in automobiles and planes due to its very light weight, and these are known as Dow metals. It is used as a reducing agent for the preparation of other metals, and in the lab it is often used as a Grignard reagent in organic synthesis. In order to burn magnesium, you will need rather high activation energy. But once this process occurs, then it is very favorable, and magnesium will burn in air with a blinding white light to form magnesium oxide, which is also known as magnesia. And it can also burn in the presence of nitrogen to form magnesium nitride. And here are the respective equations. 2 equivalents of magnesium react with 1 equivalent of dioxygen to form 2 equivalents of magnesium oxide. So this is again a very simple redox reaction. On the other hand, you have 3 equivalents of magnesium reacting with dinitrogen to form magnesium nitride, and this is also a redox reaction. Now lithium, as we have seen before, behaves in a very similar way. And if you take the magnesium nitride and you dissolve it in water, then what you obtain is magnesium hydroxide and you liberate ammonia. When heated, magnesium is a very strong reducing agent. Because of its strong affinity for oxygen and halogen, it can even reduce very stable oxide like silicon dioxide or even carbon dioxide. And here are the respective equations. And again, the magnesium simply strips off the oxygen from these oxides and liberate the respective element, in this case silicon or carbon. Here you can watch a video about magnesium burning in the presence of carbon dioxide to form magnesium oxide. Almost all of magnesium compounds contain the magnesium in a +2 oxidation state. For example, we have magnesium hydride, magnesium fluoride, and the hexa-aqua magnesium cation. Magnesium 2+ generally has a coordination number of 6, giving rise to octahedral complexes. This is the case for the hexa-aqua magnesium complex and also for the hexaamine complex of magnesium. Sometimes it has the coordination number of 4 with a tetrahedral magnesium in the center. And examples of these include the very famous Grignard's reagents. And the structure of such a Grignard reagent you can see here. So you have your magnesium center here in gray. You have your large bromide anion, and you have 2 ether molecules bound via the oxygen in red. And here you have the ethyl group, and the other ethyl group here is sticking out at the top. These Grignard's reagents are named after Victor Grignard, and again, they are very useful in organic synthesis, and there are numerous publications which deal with the use of Grignard's reagents. Here we look at some other very important magnesium compounds, for example, magnesium oxide, magnesium hydroxide, and magnesium carbonate. The annual world production of the chemical magnesium oxide, magnesia, is in the tens of megatons. It is mainly used in the preparation of mortar for construction and in medicine as a mild neutralizing agent. Magnesium oxide is produced industrially by heating magnesium carbonate, magnesite, or a mixed magnesium calcium carbonate, which is known as the dolomite. So in these reactions, you simply have a thermal decomposition of the magnesium carbonate. So by simply exposing magnesium carbonate to high temperatures, you lose CO2, and what remains is the magnesium oxide. The same reaction occurs here with the mixed magnesium calcium carbonate, and in this case, of course, you would then obtain the magnesium oxide along with the calcium oxide with liberation of carbon dioxide. Magnesium oxide can also be obtained by thermal dehydration of magnesium hydroxide, as we have seen before. So this is a magnesium dihydroxide, and when you heat it, you simply eliminate water. And this magnesium hydroxide, in turn, is obtained by precipitation from an aqueous solution of magnesium chloride, in which calcium oxide or calcium hydroxide is added. And here are the respective equations for these processes. So again, magnesium chloride reacts with calcium hydroxide, essentially under chlorido-hydroxido exchange to form magnesium hydroxide and calcium chloride. Here you can see the dehydration of magnesium hydroxide to form magnesium oxide and water. Of course, magnesium hydroxide can also be formed by treating magnesium salt solutions with a base. Now, we encounter magnesium carbonate also often in our lives. They are used as fillers in rubber, paper, plastic, paints, etc. And here you can see gym chalk, which is used in rock climbing, weightlifting, and gymnastics. And this is this white powder that people put on their hand to prevent too much moisture from sweating. Now, the carbonates of calcium and magnesium are the reason for the hardness of water. So, dependent on the concentration of these carbonates in the water that you consume, you can classify the water as soft, moderately hard, hard, or very hard water. And of course, these metal carbonates have also sometimes an undesirable side effect. For example, they can block water pipes. And of course, that leads to some damage of household items, for example, that can happen in washing machines. Now, this is the last slide on magnesium and for group 2 metals in general, and it highlights a very important process that happens in the biosphere involving magnesium, and that particular process is photosynthesis. This process is highly endothermic, so you need a lot of energy to convert carbon dioxide with water into glucose, and that obviously happens with sunlight. And you need additional ingredients. You need a chlorophyll, which could act as a catalyst for this reaction. And the chlorophyll contains magnesium. Now, the active site of chlorophyll consists of this particular complex, which contains a porphyrin system bound to a central magnesium cation. So this is a Lewis acid-base adduct, or you can also call it a magnesium complex. The important chemistry happens in this particular surrounding. Finally, you can see the structure of D-glucose, which is, along with oxygen, the product of this photosynthetic process. And this D-glucose is our energy carrier, and so we will consume food which brings D-glucose. And overall, this slide highlights again the very important role of magnesium in the biosphere.